of lecture 3, the equivalent systems, and using the echelon form, the elementary row operations, and then direct methods for solving linear system of equations using Gaussian elimination and Gauss-Jordan. So let's recall the concept of a linear equation. It's an equation of a line simply. So it doesn't include any nonlinear operator like the power of 2, the square root, the power of 3. It's only linear in, however, multiple number of unknowns. But what is important is that the powers of these unknowns is 1 raised to the power of 1 with any coefficient. The coefficient is the number that lies beside the unknown multiplied with it. For the dimension, we might deal with 2 dimensions, which is a straight line in two unknowns, which are the x and y. This will be considered as the 2 dimensions, the 2D. It might be extended to the 3 dimensions, like we discussed the plane, the full plane, extendable from all the directions. Imagine a piece of paper, and then imagine that we've extended it from all directions, from all these 4 sides. Up till where? Up till nowhere, actually, up till infinity. This will be the description of a plane, which is a linear equation in 3 unknowns. The 3 unknowns can be x, y, z, or x1, x2, and x3. And the dimensions as well can be extendable up till the 4 dimensions or more. So the system of linear equations that we will be dealing with is a system of 2 or more equations in 1 or more variable. So we'll have at least 2 equations that we need to satisfy both, and we will have 1 or more variables like we will see. This is an example of that system. This system is composed of 3 equations in x, y, and z, which means 3 unknowns. It can be 2 equations in 3 variables, or 9,000 equations in 567 variables, or any combination. In the numbers, the solution of the system that we expect is, like we discussed, it's either a no solution, one solution which we called unique, or infinitely many solutions, which this concept we will emphasize more in this tutorial. Let me give you a note here that if the number of equations is the same as the number of variables, this system is likely to have a unique solution if the number of equations is equal to the number of unknowns. This system is likely to have a unique solution. However, it can also has no solution, like we will see while solving. If the system has no solution, we call it inconsistent system. If it has one or infinite, a unique solution, or infinite many solutions, we call it consistent. This is the graphical representation like we discussed. So if we have here 2 equations, each straight line is an equation, and each equation is in x and y, or x1 and x2. If these 2 lines graphically are parallel, like this example here, we have 2x minus y equals 4, the blue line, and 6x minus 3y equals 3. So here, this first graph is for the 2 parallel straight lines which have no solution. This is in the case of the 2 dimension, and this is the example. If you notice that you will find the coefficients of the unknowns is multiplied by a factor. So in the blue line here we have 2x minus y, right? In the red line, the 2x turns to be 6x and the y is turned to 3. So if we multiply 2x minus y by what? By 3, yes, we will get 6x minus 3y. But the right hand side here is different. If the right hand side was also a multiple of the other right hand side, if this 4 is multiplied by the same multiple like we did here, multiplying by 3, so if this 3 in the red was 12, we were going to have the other infinite solution, this graph. The infinite solution where we have here the 2x minus y equals 4, and the other line equation which forms the system, both the 2 equations forms the system of linear equations. You will find it multiplied by 3, but how can we see this? 2x times 3, yes, 6x minus y times 3 negative 3y. And 4 times 3 as well is equal to 12. So the whole equation is multiple of the other. And this is the case where we have an infinite number of solution, and we have to imagine this when we see them algebraically. So if the right hand side is also multiple and the whole equation is multiple of the other, then we are an infinite number of solution. If only the right hand side is the difference and the unknowns are multiples of each other, then we are in the no solution case. However, most of the cases will have the unique solution, which is called consistent. So the consistent is either infinite solution or one unique. Regardless the dependent and independent, because we will discuss them in later in worksheets later on. Okay, so the unique solution is where we have a single point that satisfies both equations, or that is called a true value for the two equations. A true value in brief is every point in that straight line. It's true for that straight line. It's called a true value, which means that for every t, here t stands for x, so for every t, which is the x-axis, every point in this blue line is equal to 0.2t. Its d, or its output, is 0.2t. Okay, so if the graph is very easy, like we have seen now, why we don't use it? Simply because if the system is of higher degree, of a higher dimension than the two variables, the graph will be very difficult and we will need algebraic methods to solve. In the 3 unknowns, in the 4, using 4 unknowns, substitution and elimination, which you discussed, you may have discussed before in the high school, which was called simultaneous solution. Substitution was easier for small cases of 2 equations or 3. Elimination is easier for higher dimensions, and this is why this elimination method is modified and used in the Gauss, like we will see. So in worksheet 3, we need to introduce to the elementary row operations, which will enable us to form equivalent systems, like we will see in details now. To form the echelon form and know what is it, the reduced echelon form, which is substituted from the echelon form. A very simple property for a matrix, which is called the rank of the matrix. It's a single number that we will get it by a certain method. And then we will solve the linear system of equations using Gauss elimination method and the Gauss-Jordan method. So this is our system of linear equations. This is how it looked like, and this is how we ordered it, or how we are going to follow its order. So the A11, A12, A up till 1n are the coefficients. They are constants and they are well-known values for each system. X1, X2 through Xn, these are the unknowns that we are looking for. Not just to act as a solution for this equation in the first line, but to act as a solution for all of the given equations in the system enclosed by this bracket at the same time. The B's, B1, B2 through Bm are also given values, numeric values. And let's start with the first thing, which is the elementary row operations. Let's here discuss what is the elementary row operations. What are the possible operations for us to apply over the row of a matrix? So let's denote here the elementary row operations. We have basically 3 operations. Number 1 is that we can interchange or exchange. We can interchange any row, let's denote it by Ri, by Rj. Okay, and this is how we are going to describe it with the double arrow, that we are exchanging row 1 to row whatever 3, and row 3 and row 1. So this is the first possible operation. The second one is that we can multiply any row, the both sides of equation by any c, such that this c is not equal to 0. This means the c is a number. We can multiply any row by any constant. Okay, this is the second. And the third one is that we can add or subtract any 2 rows. I can add and subtract any two rows. This means that we cannot multiply two rows. We cannot divide two rows. We only can add or subtract two different rows. We can only multiply a row by a non-zero constant. And finally, we can interchange any two rows or exchange them, exchange their position. Okay, so here in exercise 1 of worksheet 3, we are asked to apply the following elementary row operations. Here, R1 for R2, which means that we are using the first operation, interchanging row 1 with row 2. So the result would be, we can write this over an arrow. This is the description of what we are going to do. So I will take row 1 as it is. You know that this is the values of row 1, right? The 0 and negative 1. I will take them to the place of row 2 and take row 2 above. This is how we applied it. Very well. Here we are asked in number B to replace R2 by 2R2. So we are asked to multiply row 2 by 2. And of course this will have a goal. We will be doing this for a reason. We will see it later. So let's copy row 1 as it is. 2, 1, 3, negative 1. And then row 2 we need to multiply it by 2. So it will be 2, 0, negative 4. It's that row 2 that we are multiplying it by 2, and then 4 times 2, which is 8. Row 3 we will copy it as it is, and now we have applied the required elementary row operation. Very good. Now in this exercise it tells us to replace row 3 by row 3 minus row 2. So this is what we are going to do. First, it seems that row 1 is unchangeable. So let's write it. And then row 2, we will put the result in row 3, right? Which is that one. Which means that row 2 will be copied as it is. So let's write row 2. And then we will put in row 3, not these values, negative 3 and 7. We will put instead row 3 minus row 2. So row 3, negative 3 minus 0, this is how we are going to commute it. Each element in the row with its corresponding. Okay, so row 3 here, this is the second element, minus row 2, 7 minus 2. So I will put here 7 minus 2. And then the next row as it is, and finally the last row as it is. Okay, and what we did here, of course, we will substitute these values. I will not write it, I will write the solution. 7 minus 2 is 5, so this is going to be 5. And here negative 3 minus 0 is negative 3, so this value is negative 3, right? So we don't have to write it again. It will be the same. This is the final result, negative 3, 5, and then 1, 4, this row as it is, and this row as it is. Now this is the matrix. Let's enclose it by the bracket, and here we are done with this row operation. So like you see, we are applying operations over rows, over corresponding rows, which means that we use corresponding elements of a row. Here we need to replace row 2. This is the result, where we will put the result of this operation. Row 2 plus 3 row 1. So we need to multiply this row 1 by 3. But row 1 itself as an outcome will remain as it is, because here the solution is mentioned to be added to row 2. So the solution of this arithmetic expression will be added to row 2. This means that row 1 is what is as it is. It will be just dropped like this. The solution we need to change in row 2. So let's keep it, and then we can copy row 3 because it's unchangeable as well. Okay, now for row 2, we need to add row 2, its elements, plus each corresponding element in row 1 multiplied by 3. So it's beneficial to try to multiply row 3 by row 1, sorry, by 3. So this is 0 times 3, 0. This is 1 times 3, that's 3. And 3 times 6, this is 18. 3 times 4, which is 12. And 3 times 0, which is 0. Now we directly, I have now commuted this part. 3R1. 3R1. You can make it with a pencil over the exercise sheet. for yourself and then add it to row 2. Let's add all corresponding values. So 0 plus 1, 3 plus 2. Each two corresponding elements in the 3 row 1, in the 3R1, this is the 3, this is the 3R1. We need to add it with its corresponding from row 2, right? So it's 3 row 1 and row 2. And here, 3 row 1 and row 2. Let's add the results. 0 plus 1, this is 1. 3 plus 2, this is 5. 18 minus 1, that is 17. 12 plus 5, this is 17. 0 minus 2, this is negative 2. And here we go. Now we have applied the stated elementary row operation, which was to put in row 2 the row 2 plus 3 row 1. This is the elementary row operation required. So this means that row 1 and row 3 are unchangeable. So we copied them at the beginning. Okay, let's apply the change in row 2 then. Row 2 will be 3 row 1 plus row 2. So we take row 1 multiplied by 3 in order to be ready with the values. Instead of saying, this is 0, 0 times 3, and then the result, the imaginary result that is in our minds, to add it to row 2, apply this for all these values. So in order to prevent any mistake, we might do this with a pencil to denote the 3 row 1 above row 1, and then directly we can add simply with our eyes the 3 row 1, the new result, plus row 2. Okay, so that was for exercise 1 and the elementary row operations. It's very easy when we notice it. In exercise 2 of this worksheet, we are asked to reduce the following matrices to their echelon form. Okay, let's have a look over the echelon form, and we need to apply this over number C. Let's apply it over number C. Okay, we will solve it in number C. Let's first know what is the echelon form. The echelon form is a matrix form. So the echelon it's something done or obtained systematically. So if we have any matrix A11, A12, A13, and then A21, A22, A23, and then A31. For example, it's a 3 by 3. And finally A3 by 3. So this matrix, we are going to apply elementary row operations that we have just learned over this matrix in order to reach this value. We need 1 at the first element, and then we need zeros below. Okay, however, this value, we will keep it as it is. We will ignore it. We don't have any restriction over the value A12 and A13. Okay, our scope is to find A11 to turn it into 1, and we will do this using the valid elementary row operations, not any arithmetic operations that might pop in our minds. We have to know what we are doing, and we have to write it to indicate which operation we are using. And then we need this value to be 1 as well, and below it's 0. We need this value to be, however, we don't have any restriction over A23, and then we need this value to be 1. This means that we can have something like this: 1, 0, and for example 3, and then 0, 1, negative 1, 1, 0, 0. This is an echelon form. It's a valid echelon form, right? What else? We might have 1, negative 7. What about this value? 1, negative 7, 0, 0. Is this echelon form? Actually, it is an echelon form. What we have tested now here is the first element with the letter, if you remember it, and then the second main diagonal element here, it's 0. So this means that this value can be 1 or 0 actually, and this as well can be 1 or 0. But we will try to keep always the first element into 1, the first element, and this element is very effective in the solution. Okay, like we will see now. So here now this system as well is in echelon form because all of the main diagonal elements are 1s, and below the triangle below this elements, this triangle below these elements is 0s, right? So as if we have swept the values or eliminated the values. This is the extension, as I told you, for the elimination technique, the that we will be using now. So let's not talk a lot and let's solve number C. Now we need in number C to get that echelon form. So what's the first step? We need this value to be 1, right? Using one of the elementary row operations, which is to interchange any two rows. We can multiply any row with any non-zero constant. We might add or subtract, or like you see, we may combine the last two operations. We might combine the last two, so you can multiply any row by any non-zero value and then add it or subtract it from a different row. These are the elementary row operations that we have just used. Very well. We need this 2 to be 1. It's obvious that we have two 1s below it. So we might use row 3 and row 1 and do what? Yes, we might apply the exchange. Row 1, exchange it with row 3. This is how to indicate what we are going to do. And this means that we will take the values of row 3 up, and then row 2 will be unchanged. It will be copied as it is. And row 3 now we will be at the bottom of the matrix. So this is what we did. Now we have fixed the first value. Very well. We need to use this value in order to eliminate the elements below. So I need to eliminate this 1 and 0 using that one. I can apply these two operations at one time. Let us do it. How this one would be 0? Using that one through one of these operations. To drive it to 0, we cannot multiply it by 0 like you see here. So multiplying by a constant, it has to be non-zero. So this is forbidden. To interchange, okay, we don't have any corresponding, we don't have any 0 element in that column to interchange any two rows, right? So this is as well will not help. What about number 3, operation number 3? We can add or subtract the value. So if this one is subtracted from that one, and the result to be set where? In row 2. This means that we have eliminated this value. So we might indicate that in row 3, in row 2, what we are going to do, we are going to set row 1 plus minus row 2. Okay, we might also write it in a different form, which is easier. The result will be in row 2. So I will state row 2 first. Okay, and then multiply it with a negative. Okay, and then so it's negative row 2 plus row 1. This is another way to write the elementary row operation. Let's apply it. Okay. So here I have row 1 as it is. Row 2 is multiplied by negative and then added to row 1. So negative row 2 plus row 1. We can add it here also with a pencil. So it's negative row 1. This 3 is multiplied by negative. The 0 is as it is, and this 5 is multiplied by negative 5. Now we are adding this negative row 2, which was written here, with row 1. Okay, let's fill it directly. Negative 1 plus 1, oh, that's the 0 that we seek. Negative 3 plus 1, this is negative 2. 0 plus 1, that is 1. Negative 5 plus 2, this is negative 3. Fine. Now we have done what we wanted with a valid operation. Let's do the same with row 3. We can do it like I told you at the same step. So in row 3 here, we need to eliminate this 2 using that 1. Okay, using that 1. This means that we can multiply this row 1 by negative 2. Right? We can multiply row 1 by negative 2 to becomes, it will become negative 2, and then add it to row what? Add it to row 3. Okay. And then add it to row 3. So we will take this row 1 multiplied with negative 2. Multiplied with negative 2, it will be negative 2, and here negative 2 times 1, negative 2, negative 2 times 1, negative 2, negative 2 times 2 is negative 4. And then directly we can add the result of row 1 into row 3. So it's negative 2 here, this negative 2, plus that 2. It will be 0. Okay, that negative 2 minus 1. This is minus 3. Negative 2 again plus 4. This is 2. Negative 4 plus negative 1. This is negative 5. Right? So this now we have we are done with column 1, the leading element, which is called that element. The main diagonal elements are called pivots or leading coefficients. So the below the first leading coefficient is zeros, and now we need to move to column 2 to the leading value or the leading coefficient of row 2. This is the second main diagonal element here, which we call it A22. We need to turn this value into 1. Again, using one of the valid elementary row operations. Can we interchange? We are afraid of interchanging this 1 above it. This will mix up what we have already did. We'll take this 1 below, and then the 0 will be up. Okay, so we don't want to go backward. We are working like from left to right. So this is how we think, in that direction. We need to fix it in that direction. So this negative 2 need to be fixed with another operation. We can multiply it with a value. Addition or subtraction will be more complicated, but we can directly multiply this value by negative 1 over 2, right? So if we have taken here row 2, multiplying it by negative half, this negative half multiplied by negative 2 will make it 1, right? This is what we need to reach in that element. We cannot apply it in that element alone. We have to apply it throughout the whole row. So let's apply the row operations. This is why it's called row operation. We have indicated what we are going to do now. And we have no change for row 1. So we will write it as it is. And then row 2 multiplied by negative half. The 0 will become 0 as it is. This is 1 now. The 1 times negative half is negative half. And then negative 3 times negative half is 3 by 2. Right? The last row is unchanged as it is. Okay. Now we are done with what? Now we are done with some leading coefficients, which is the first one, the first leading coefficient of the first column, and then the second leading coefficient is 1. What's left is, like we see here in that example, we need to eliminate the element below. So we need to use this 1 to eliminate that element below it, this negative 3. How can we do this with one of the valid elementary row operations? We will say what? We will say that we would multiply row 2 because we are going to use row 2, right? So we are going to multiply it with the multiplicative inverse of -3, which is 3. So the additive inverse, sorry, the additive inverse of -3, which is 3. So the additive inverse is the number that makes in addition of a certain number 0. So the additive inverse of -3 is 3, because -3 plus 3 is 0. Okay, I'm just reminding you the property. So multiply this one by 3 and then add it to row 3. It means that we have no change for row 1. So I will write it as it is. The result here will be placed in row 3. So this is what we are using. This is the row that is used. And this is the row of the result. We might fix the operations representation using this meaning. And then, so the result is set to row 3, which means that row 1 is unchanged. -½ and this is the 3/2 as it is. Okay, what about row 3? We need to add the value of row 3 times or plus 3 times row 2. So we can come here to row 2 and multiply it by 3. This will be 0. Multiply this by 3, it will be 3. Multiply this with 3, it will be -3/2. Multiply this with 3, it will be 9/2. And then we need to add this 3 times row 1. 0 times this 0, this is 0 here. What we are doing now with this order guarantees that none of the values that we have worked on would be mixed up or would be turned to any number. So it's like sweeping for the matrix. Now 3 plus -3, yes, this is 0, and then -3/2, which is -1.5, plus 2, which is half. And here we have 9/2 minus 5, which is 9/2 minus 5 is -½ Okay, now let's check what we did. We have 1 in the main element diagonal, in the main diagonal element, or the first leading coefficient, and then the second leading coefficient is 1 and below it's zeros. What about the last leading coefficient? That one we need to set it to 1, so we will simply multiply 2 times row 3. This is how we can indicate it. This is the non-zero constant that is that was suitable for applying what we needed. So I'm copying row 1 and row 2 as they are without any change. We need the change only to be applied over row 3. So multiplying this half with 2 is going to be 1. Of course, multiplying half with these zeros, they remain as it is. And finally 2 times -½ is -1. And here we go. This is the echelon form. Okay, how can we check this? Simply, we just go with the leading values or the main diagonal elements. The main diagonal elements are 1s. Perfect. The triangle below them is zeros. Fine. That's it. Okay. Let's do it again. But we will be more, we'll try to be more quickly. So let's take number D from the worksheet. And then try to think, using the elementary row operations, how can we reach out the echelon form. Now we have here 1 in the first main diagonal element, right? And we have 1s below. So we might use one of these ones below, right? We might use any of the ones below. Let's use the 1 and 3. Let's use this row. Okay, I have taken D. That's fine. So let's take this row. This row is number what? 1, 2, 3, 4. This is row 4. Right? So we will take row 4 and replace it with row 1. So we are exchanging row 1 and row 4. Right? This means that row 4 will be raised up. 1, 3, 0, 5. Row 2 will be unchanged as it is. Row 3 unchanged as it is. And row 4 will be row 1. That's it. This is the operation that we have applied, reaching our first goal. Now we need to use this one in order to eliminate the elements below it. So we need to eliminate this -1 first. Now it's -1, they are both additive inverse. So we might say that row 1 that will be added to row 2 directly. This means that this is the used row and this is the result, where the result will be set. The result of this arithmetic operation, okay? So the first row is unchanged. We will copy it. The second row, oh, this is the result. This is where we are going to put the result of this arithmetic operation. Row 1 plus row 2, this is 0. It's a direct addition. 3 plus 2, yes, this is 5. 0 plus 2, that is 2. And 5 minus 2, this is 3. Very well. Now, at the same time, to save time and effort, instead of copying, we can, of course, copy the rest of the matrix and do it in a separate step. But just to save your time, we can do it at the same step to eliminate that one using the 1 in row 1. Now we will use the row 1 and multiply it by negative and then add it to row 3. We will multiply this row 1 by negative, so it will be -1, -3, 0 times -1, 0, and then -5 because it's 5 times -1. These values will be directly added up to row 3. So it's -1 plus 1. This is 0. -3 plus 0. This is -3. 0 plus -1. That is -1. -5 plus 3. This is -2. Okay. Now the last element here, it's by itself 0. So we need to apply nothing. Let's just copy it. Of course, not every operations can be applied in parallel. So now we were setting the results into different rows in row 2 and in row 3. These are the rows that are affected by our operations at the same time, and they are different. Okay, so the results got to be set in different rows. Now let's move to tracing the leading variables. Here we have this one coefficient, the first main diagonal element. This 5 is the second main diagonal element. We need to set it to 1. So how can we do this? We have 1 here below it, which we can use it in the interchange because it will not mix up any of the first column zeros, right? So as we said, we are thinking in that direction and we are trying to be as simple as we can. So if this one will be exchanged with that 5, this means that these two zeros will be exchanged as well, and this will make no problem with us. So we can go for it. Let's exchange row 2. The 5 is in row 2 with row what? With the last row, which is row 4. In order to reach setting the second main diagonal element into 1. 1, 3, 0, 5, and then 0. Instead of 5, it will be 1, 1, 0. This is row 4. Row 3 will be as it is without change. And then we will take the row 2 instead row 4. Right? Very well. Now let's trace quickly what we have done. Now what is done is that the leading coefficient, the first one is 1, below it zeros. That one is 1, but below it is not zeros still. So let's do it in one step also, but in parallel. We need that -3 to be 0. Using that one, don't forget, using that recommended, and it's very important to go in the same pace and in the same steps that we are dealing with now. So this one will be multiplied by 3. 3 times row what? This one lies in row 2. So we will multiply 3 by row 2. And then add it directly to this negative 3, which lies in row 3. So we will write it like this, plus row 3. This means that row 1 is unchanged. So let's copy it. Now row 2 is unchanged as well, because the result is set in the second. So here is the result. Okay, row 3 now is the one which will hold the result. Let's multiply row 2 by 3. So this is by 3 times 0 is 0. 1 times 3 is 3. 1 times 3 again is 3. 0 times 3 is 0. Now add it, 0 plus 0, that is 0. Yes. 3 plus negative 3, this is 0. And 3 plus negative 1, which is 2. 0 plus negative 2, which is negative 2. Now we have applied it successfully. Let's apply it over this other row, also in parallel, before closing this matrix. We need to set the last row, but instead of taking it, writing it, and then do it in a separate step, which you can do it at the beginning, we can do it at the same time in parallel. So now we need to use this one to make that 5 0. So we will multiply that one. That one lies in row what? In row 2. So I will indicate row 2. Multiply it with negative 5. And then add it to row. Which row is this 5 included? 1, 2, 3, 4. Row 4. Okay. The result is obtained and written in row 4. So here where we will write the result. This is one of the many ways that we can indicate the elementary row operations. Okay, so I meant that this is an arrow, and this operation above it, and this operation below it, below the same arrow. Okay, so this is what is meant. Okay, now we need to set the result, this operation, which is multiplying row 2 by 5. So we need to multiply 0 times 5, this is 0. And this 1 times 5, that is 5, sorry. 1 again times 5, this is 5. And 0 times 5 is 0. Now we can add these values directly. We have multiplied row 2 by negative 5. Right, so this is negative 5, sorry. Here, by negative 5. So I multiplied it by negative 5 and the zeros as they are. Now let's add this negative 5 times row 2 that we have indicated beside the row values and add it to row 4. 0 plus 0, this is 0. Negative 5 plus 5, that is 0. Negative 5 plus 2, this is negative 3. And then 0 plus 3, this is 3. Now let's trace what we have done. This is 1 below with zeros, very well. 1 below with zeros, wow. This other main diagonal element, which is a leading coefficient for the system, like we will see when we discuss Gauss elimination technique. This 2 needs to be 1, need to be set to 1. So simply we can use one of the valid elementary row operations. We can add any value, yes, but it will take more time. The simplest thing to make a value 1 is to multiply it with its multiplicative inverse. So if it's 2 multiplied by half, if it's 1 over 3 multiplied by 3, negative 3 over 9 multiplied by 9 over 3, or any combinations. So here we will multiply this row. This 2 is included in row 3, so I will indicate row 3. Multiplied by what? Multiplied by half, because half times 2 is 1, which we need to do. This has to be written in a row. And then the result after this row, the first row is unchanged, so it will be written and copied as it is. Again, row 2 is unchanged. Okay, row 3 now is the one to apply the operation of multiplying 0 by half, this is 0, 0 by half again, 2 times half, this is 1, and negative 2 times half, this is negative 1. Perfect. And the last row is to be copied as it is without any operation. Now we need to trace what happened quickly. So here we have the first element in the main diagonal. Yes, it's 1 and below it zeros. This one is 1 and below it zeros. The third main diagonal element is 1, but below it is not zeros. So we need to apply an operation, a valid elementary row operation, which would enable us to do it. Of course, we need to do it using that one. So I need to using that one to turn this negative 3 into 0. So I need this one to multiply it with 3, right? And then add it to the negative 3. Okay, negative 3 lies in row what? In row 4. So we will add it to row 4. This 3 will be multiplied by the 1 which lies in row 3. So it's 3 times row 3 plus row 4. It's very significant to decide which operation you are going to do, and you will get used to it. It's very systematic and direct. So now the result is to be added to row 4, which means that row 1 is unchanged. Let's copy it. Row 2 as well will be unchanged. Let's copy it. Row 3, again, it's unchanged. So we will copy it as it is. Now row 4 is the one to be changed and set to 3 times row 3. So this row 3 needs to be multiplied by 3. It's again 0 here. Multiplied by 3, 0. Multiplied by 3, this will be 3. Multiply this with 3, this is negative 3. Now we can directly add 0 plus 0. Yes, that is 0. And then 0 plus 0 again, this is 0. It's an elementary row operations. 3 plus negative 3, that is the 0. Negative 3 plus 3, it's again 0. So now we have this form. Let's trace it to find out what we reached. We have 1 in the first main diagonal element and below it zeros. We have 1 in the second main diagonal element and below it zeros. 1 in the third main diagonal element and below it zeros. The last element turned out to be 0. It might have been 1 or 0. So if it's any number, we will multiply it by 1 over that number to reach the 1. If it turned out to be 0, like here in this case, we will keep it as it is. And this form is an accepted echelon form. So this is one of the echelon forms. And like you discussed in the lecture, the echelon form is not unique. The echelon form might have many figures. Okay. Now let's move to exercise 3, which is the reduced echelon form. What's the reduced echelon form? I will copy the exercise and then discuss it. This reduced echelon form, we need to discuss exercise C. Let's do number C. Let's do number B and C, and the rest to be left to you as an exercise. We just need to get the idea, because this is what we are going to use in solving using Gauss and Gauss-Jordan. Then Gauss and Gauss-Jordan will be discussed in 1 minute, because we already know what they mean by every step. We already know what is the echelon form, what's the reduced echelon form. And this is what is required till this exercise. So we need to reduce the following matrix to their reduced echelon form. So the reduced echelon form like we said, we might have a full matrix here. We will need to set the first main diagonal element into 1, below it zeros, like the echelon exactly, and then we need the second main diagonal element to be set into 1. Okay, and in this case we need below it 0 and afterwards above it 0. Okay, and the last main diagonal element to be set to 1, and we will try to make the above elements zeros as well. So this is one form. It's like the unit matrix, if you remember, the one of the matrices. That's multiplying it with any matrix from left or right brings up the same matrix. Okay, so we need to reach such a system. It's not only this system. If one of the other main diagonal elements, like that one, the second, the 2, 2, or the 3, 3, turned to be zeros, so if we might say or, I will say it or, and then we have something like this: 1, 2, 0, 0, 0, 0, and then 0, 3, 1. This form is what? Let's trace it. We have 1 in the main diagonal element, fine, and below it 1s. And we have 0 in the second main diagonal element, which means it's not leading for that system. This coefficient, of course, we know that we will get the coefficient matrix like we did at the end of the last worksheet. So this matrix will be always denoting the coefficients of the unknowns or the variables. This coefficient is not leading because it turned to be 0. Not 1. If it's 0, this means that it's not leading. It's not one of the basic variables, like we will see. So we will neglect above it and below it. We will not need to eliminate the elements above it nor below it. So if we have non-zero elements above it and below it, we are still in an echelon form. The last main diagonal element is set to 1. Okay, if it's 1, then it's significant. The main diagonal element in row 3 here is 1. So this column will be significant, and it's one from the basic variables for that system, which means that the above elements got to be 0. As if the echelon form is interested in the below triangle, the triangle below the main diagonal elements, it needs to eliminate it to 0, while the reduced echelon needs to eliminate the elements above as well. So it eliminates the elements below and add to it by eliminating the elements above. So here, this was one of the forms. If we are having, as a last example, if we have a matrix that looks like this, and then we have 0, 3, 0, is this echelon form a reduced echelon form? This is our question. Let's trace it. Okay, so in the first main diagonal element, it's 1s and below it 0s. Very well. Let's move to the second. It's 0s. So we don't need to eliminate either above it or below it. Let's move to the second. Oh, it's 0s again. So we don't need to eliminate above it. So this form is reduced echelon form. Yes, it is reduced, because the pivots or the main diagonal elements, if it's 1s, we will be interested in eliminating above and below. If it's 0, we will neglect them, and they will not be significant to the system. Okay, let's do this here with part B in order to get to this idea. So in part B here, we need the first element. In part B, we need the first element, this to be 1. Right? So let's simply exchange row 1 by row 2. And here we will have 1, negative 1, 3. And row 2, which is negative 1, 3, negative 5. I interchanged now the two rows. What else? We need to use this one in order to eliminate the element below it. So using this one, we need to eliminate the element below it. We will take row 1 as it is and add it to row 2, right? Because they are already additive inverse to each other. Their addition is 0. So row 1 will be without change. Row 2 will be added to row 1, and the result of this arithmetic operation will be resulted in row 2. So here we have 0, negative 1 plus 3, this is 2. and 3 minus 5, this is negative 2. Right? What's left now? We have this 1 below it 0, fine. We need this 2 to be 1, right? So let's multiply it by, as we said, that if we need any value to turn into 1, it's better to multiply it with its additive inverse. So it's half times rho 2. Now rho 1 is unchanged, and rho 2 will be multiplied by half. Write it above the arrow. So 0 times half is 0, 2 times half is 1, half times negative 2, this is negative 1. Very good. Now this form is what? If we have traced the main diagonal elements like we did also always with this ladder, we will find that the main diagonal elements are 1s now. Perfect. And the triangle below is 0s. Then this is what? This is echelon form. But what is requested here is to move to the reduced echelon form. So let's continue using that one in the reverse direction. We will use that one in order to eliminate the element above. So always we are dealing, or we are using the main diagonal elements. So here, using that one, let's eliminate the negative one above it, which means that the last row or the second row will be as it is, the 0, 1, negative 1. And we need directly to add these using row 2. So we will use row 2 as it is and add it to row 1. Right? This is the operation that we are going to do. And the results are set into the second mentioned row. So here 0 plus 1, this is 1. 1 plus negative 1, that is 0. Negative 1 plus 3, this is 2. And this sequence, as I told you, guarantees that you will not mix what you already reached from fixing the values in the right side or in the first column, I mean. Okay, which we can call it the right side values here. So here we have in the first main diagonal element 1 below it 0, the second main diagonal element 1 below it, and above it 0. We don't have anything below it. So in this case, this is the reduced echelon form. You will tell me, what about the last column? Right? We will neglect it. We are just working in the main diagonal elements and around them, because these are the significant elements like I told you in the last tutorial. Okay, let's do the same with number C, or we can leave this as an exercise and let's jump to the rank of matrices. You will apply the same and I will do with you the same in solving using Gauss and Gauss-Jordan. So it's better now, instead of doing repeated operations, let's get to the rank of a matrix and we will solve number E. So the exercise here says transform each matrix of its reduced form into, okay, I need to solve number E. Let's take number E. So here, this is number E. Transform each matrix of its reduced echelon form and hence find its rank. So we need to reduce this matrix first into its reduced echelon form in order to be able to get the rank. I will tell you the definition of the rank first. So the rank by definition is the number of non-zero rows, you will see it, in the echelon form. Okay, So now we are requested to get the reduced echelon form. Working on element number 1, the A11, it's 0, sorry, and below it we have -1. So we might exchange these two values, right, in order to have the -1 in the first row, and then multiplied by -1 will be easy. So here let's say that we are exchanging row 1 with row 2. Okay, so we will have here the -1, 3, 2 and -6, and row 1 will be below it 0, 1, 1, -1, and row 3 0, -2, -2 and 2. Very good. We need this first main diagonal element to be 1, not -1, so we can multiply row 1 by negative, and hence we have 1, -3, -2, and this -6 will be 6, and the other rows will be unchanged, so we will copy them as they are. Okay, now we have the main diagonal element. The first one is 1, and below it zeros. Very well. The second one is 1. We need to set below it zeros, so let's make this 0. We need to let this element to be 0 using that element in the main diagonal. So using A22, we need to make this value 0. So we will multiply this one by its additive inverse. What is the number that adding it to -2 will result in 0? Of course, -2 plus 2. So we will multiply this one with 2. I will say 2 times this element. I will not multiply it only with this element. I will multiply it with all of the elements in the row, and this is why we denoted it's 2 times row 2. And then what? We will add it to this element -2, which lies in row 3, so we will say plus row 3. We will do now this elementary row operation and see the outcome. The first row is unchanged, so we will copy it, because as we know that the result will be set here in the second row, in the third, sorry. So the first row is unchanged as well, and the third row will be the changed one. We will multiply 2 times row 2, so 0 times 2, 0. 1 times 2, 2. 1 times 2, 2. -1 times 2 is -2. Now we directly add 0 plus 0, 0. 2 plus -2, this is the 0 that we needed. 2 minus 2, it turned another 0. -2 plus 2, this is again 0. And therefore, now what we have reached is as follows. The first main diagonal element is 1. Below it, zeros. Very well. The second main diagonal element is 1. Below it, zeros. And the third main diagonal element is 0. So we are not interested in it. We will ignore it. This means that we are in echelon form. But we needed the reduced echelon form, right? So we need to eliminate that -3 because it's in a column where the main diagonal element is 1, not 0. So we need this -3 to be 0. Using that one, please, using that one, we need to eliminate that element. So this one will be multiplied by what? So that what that we are looking for, adding it to -3 will be 0. So 3 plus -3 is 0. So we are multiplying this one with 3. Okay, 3 multiplying it by that one. That one lies where? Lies in row 2. So it's 3 times row 2, and then directly added to row 1. And this time the result, it will be set into row 1. So we will copy row 2 before we work on it. And the last row as well, we will copy it because it's unchanged, zeros. The only change here will occur in the first row, where it would hold 3 times row 2. So 3 times 0, 0. 3 times 1, 3. 3 times 1, again 3. 3 times -1 is -3. Let's directly add this 3 times row 2 plus row 1. So 0 plus 1, this is 1. 3 plus -3, this is the 0. 3 minus 2, this is the 1. Or 3 plus -2. -3 plus 6, this is the 3. right? Now let's trace what we have done. First main diagonal element is 1 below its zeros. The second main diagonal element 1 above and below zeros. The last main diagonal element is 0. So we ignore it, or we are not interested in turning the elements above it to zeros. We just ignore it, neglect it. Therefore, we have reached the reduced, it's the reduced echelon form. Okay. We need then to get the rank, because it was indicated here to find the reduced echelon form and hence find the rank. And we said that the rank is the non-zero rows in the echelon form. The non-zero rows versus what? This non-zero, if you need to understand it, it versus its opposite is the zero row, right? So we need to find the not zero row, the negative of zero rows. This first row is not a zero row, right? So it's called a non-zero row. Simple. This is non-zero row number 1. That second row, again, it's not a zero row. So it's non-zero row number 2. That last row, no, this is a zero row. So it's not a non-zero row. Now, how many non-zero rows do we have? 2, and therefore we will indicate that the rank of this matrix, the rank here, is equal to 2. The rank here is equal to 2 because we have 2 non-zero rows. Perfect. Let's move to exercise 5, where we are going to use the Gauss elimination technique to solve finally the system of linear equations. And let's solve quickly some problems. So here we are in exercise 5. I will take this there. Okay. What happened? Sorry. Okay. So now we need to solve this system, or these systems. We will pick some of them to solve them using the Gauss elimination, which is an extension for the elimination method that you have used before in the high school. So the Gauss is a German scientist. The double S is written like this, the Gauss elimination, or you might write it as double S normally. So the Gauss elimination states what? It has a specific steps that we will follow. In step number 1, we need to set what is called the augmented matrix. And the augmented matrix will look like this, A of B, like we will see. In step number 2, we need to use the elementary row operations. Why? To reach the echelon form. So we need to get the echelon form using the elementary row operations. In step number 3, what we need to do, we will apply the back substitution in order to read the solution. And this step number 3 will differ according to the type of solution. So here, according to the type of solution, our behavior will change according to the type of solution. Let's start with number 8, where we have this system, this simple system, 2 equations in 2 unknowns. What we need to do is to transfer it into its matrix form. So we need to write the matrix form like we did at the end of last chapter, of the last worksheet. We said that there is a matrix A, that's a matrix of coefficients, right? And it will include the coefficients here. What is the coefficients of the first unknown? 2 times x and negative 3 times x. So we have 2 and negative 3. The coefficients of the second unknown, negative 2 y, and here we don't have y. So we say that it was multiplied by 0, right? So this A multiplied by the vector of unknowns, which is here x and y, equal to the right side, which is the results or the B's, negative 6 and negative 6. So this is the matrix form. That is A and the unknown vector x, and this is the B vector. This is a vector and that is a vector, right? So you can write it now in the form AX equal B. This is the linear system in part A, right? The Gauss elimination said that we have to set the augmented matrix, which is A of B. Now we don't need the problem itself. We need to set A of B. So I will write the matrix, this coefficient matrix, off. I will write this off, and this off indicates the equal. It means that what lies next is the B vector. Now I formed a matrix of 2 rows and 3 columns. I will work on this using the elementary row operations in order to reach the echelon form. Of course, we didn't forget the echelon form. We need to use this element and make it 1, right? So we can simply multiply it by half. So we will multiply by half row 1. It will be 2 times half, which is 1, negative 2 times half, which is negative 1, and finally negative 6. Again, this is the last element in row 1. Negative 6 times half is negative 3. So we have here negative 6 divided by 2. What about the second row? We will leave it as it is. We cannot apply 2 operations in one row. What do I mean by applying 2 operations in one unknown? In one row? I mean that now we have this element set to 1. Perfect. We need to eliminate what's below using that one. So I will use this one. This is why I can't apply 2 operations in one row. The operation to be applied in the outcome of the first elementary row operation, half times row 1, and then we will follow it by this negative 3 needs to be eliminated. So it's need to add it to be added to 3. Therefore, we will multiply 3 by row 1. And this will be added into row 2, right? This means that the results will be set to row 2. So row 1 will be as it is. And then 3 times row 1. Let's multiply row 1. This 1 times 3, it's 3. Negative 1 times 3, this is negative 3. Negative 3 times that 3, this is negative 9. And then add the result into row 2. So 3 minus 3, this is 0. Negative 3 plus 0, this is negative 3. Negative 9 minus or plus negative 6, this is negative 15. Okay, this is very good. What's left is that this negative 3 needs to be 1. So we will multiply. This negative 3 lies in row 2. I will multiply it by negative 1 over 3. And therefore, the first row will be as it is. And the last row, 0 times negative 1 over 3 is 0. Negative 1 over 3 times negative 3, this is 1. Negative 1 over 3 times negative 15, that is 5. Right? So now, this form that we have reached is what? The first main diagonal element is 1, below it's 0. The second main diagonal element 1, and we don't have other elements. Therefore, we have reached the echelon form. And we are done. So the last step here is to back substitute. Let's do the back substitution. The back substitution means that we will read back the rows into equations. We will take this matrix into equation again. Remember, the first column was representing the coefficients of what? Of the first unknown, right? Which was here indicated as x. So these were the coefficients of x. This column indicated the coefficients of y. And this bars means the equal. This will make it easy to turn it into equations, and please go from bottom to top. So let's start by reading row 2. This is the last row we have here. It's 0 times x. 0, this is the coefficient, times x. This is 0. Plus 1 times y, which means we have y, equal. This bar, moving by this bar means equal, equals what? Equals 5. So we can say that y is equal to 5 directly from row 2. And from row 1, we have 1 times x, which is x, and then plus negative 1 times y. I can write it directly minus y, and then equal, because I'm going to pass by this bar, equal negative 3, right? Now we know that y is equal to 5 from row 2. We can substitute this here. So this y is 5, which means that x is what? Is the negative 3, and take this negative 5 into the other side, plus 5, which means it's equal to 2. And therefore, we have what? And therefore, the solution is x, y is equal to, the x is equal to 2, and the y is 5. This is the x vector, which is the vector of unknowns, right? Now they are knowns, and this solution is of what type? Yes, it's the unique solution. Let's have a look over another example. If you need to pause and take a break, it's fine. But we are almost done. I want to solve with you number B, because it has a different type of solution and it's very quick. So number B here, the system is x minus y equals 5 and 2x minus 2y equals 3. Now we need what? We need to do all of the steps again. Simply, the first step is to get the augmented matrix. Okay, I need this pen. So first we will set the augmented matrix, which is the matrix of coefficients. Directly I can write it, the first column for x coefficients, which is 1 and 2. And the second column for the y coefficients, which is negative 1 and negative 2. And then I will do the bar and write the b's, or the results. This is the augmented matrix. This is the A by B. Okay. In step number 2, I need to use the elementary row operations in order to reach what? Only the echelon, not the reduced. In Gauss elimination, we need to reach the echelon form. This is the Gauss elimination. This is the Gauss elimination technique. Okay. So the echelon form will be reached how? Let's get it with a different color. That element is 1. Perfect. We need to set or eliminate the element below. So I will multiply this one, which lies in row 1, by negative 2. Why? Because in adding it to 2, which lies in row 2, it will turn it to 0. So here row 1 is without change. Row 2, yes, this one will carry a change. Let's indicate this operation first. Negative 2 times row 1. So negative 2 times 1, this is negative 2. And then negative 1 times negative 2, this is 2. 5 times negative 2, this is negative 10. And then we will directly add negative 2 plus 2, this is 0. and then 2 plus negative 2, this is 0 again. Negative 10 plus 3, that is negative 7. Now what have you got here? We have 1 in the first main diagonal element below with zeros, and the main diagonal element turned to 0. So we will neglect it. We will not need to eliminate the elements above it, below it for the echelon form, or above it and below it for the reduced. So here we have reached the echelon form successfully. Let's move to number 3. So step number 3 is to back substitute. And as we said that we will substitute from bottom to top. What's the last row? It's row 2. Let's read row 2 and let's remind ourselves that these were the unknowns, the coefficients of x, and that was the coefficients, that column of y. This bar means the equal. So reading row 2 directly, 0 times x, 0 is eliminated, 0 times x is 0, plus 0 times y, 0 times y. I can write it like this if you can't figure it out. So times plus 0 times y equal negative 7. So of course 0 times x is 0 and 0 times y is 0. So this output 0 equal negative 7. Now is 0 equal negative 7? This is a false statement in mathematics. And if we reached a false statement, this means that there is a contradiction in the system, and this system has no solution. Has no solution. Now we have this exercise number D in the same exercise for getting the solution using the Gauss system. So using the Gauss elimination method or technique, we need to set the 3 rules or the 3 steps that we have discussed. The augmented matrix is the first thing, A of B, to write the matrices of the system in that form. Now we have how many unknowns here? We have x2, x3, and x1. So we have 3 unknowns. We need a column for x1 coefficients, a column for x2 coefficients, a column for x3 coefficients, the bar, and the b's, which will be definitely negative 1, negative 6, and 2, as indicated by the system, the given one. Now let's write the coefficients. In the first equation here, we don't have an x1 term, which means that it was multiplied by 0. We have x2, which is 1, yes. We have x3, which is 1 again. Okay, the second equation is negative 1 times x1, 3 times x2, and 2 times x3. The last one, there is no x1, so it's 0 times negative 2 times x2, and then negative 2 times x3. Perfect. So that is the augmented matrix. Now we need to work on this augmented matrix using the elementary row operations in order to find the echelon form. Right? Which will be what? Which will be ones and zeros below, because we have here three system. We don't have to work on the above the main diagonal elements because we will not use them, and then we need that element to be 1 and below it's 0. This is not important as well, and this can be 1, and whatever the values here we will deal with. Right? So this is what we are seeking. And to be more specific, actually this value, the main diagonal element, this value is accepted as 1 or 0, and this one as well is accepted as 1 and 0, right, like the previous system. Okay, now let's try to reach it. We have 0 and below it we have 1, so let's exchange or interchange these two values, and we can't change these two values alone. We have to apply it for the 2 full rows. So we will exchange row 1 with row 2, and therefore we will have negative 1, 3, 2 off. negative 6, and then we have below it 0, 1, 1, and negative 1, and finally we have 0, negative 2, negative 2, and 2. Okay, now we need this negative 1 to be 1. So we will multiply row 1 by what? By negative 1. And hence we have 1, negative 3, negative 2 of 6, negative 6 times negative 1, and then 0, 1, 1. All the other elements are of no change. And as you can see here, we have in the first column 1, in the first element here, this is 1, and below it, they are automatically zeros. So we will do nothing. And also the second main diagonal element is 1, but below it is not 0, so we need to use this one in order to eliminate that element. We need to eliminate the negative 2 to set it to 0. So in this case, we need to add it to its additive inverse, which is 2, because 2 plus negative 2 is 0. Okay, so we will multiply this one by 2. 2 times that one. That one lies in which row? In row 2. And then add it directly to row 3. Right? So what we need to do, we set it first. I need to have a 2 for this negative 2. If it was 2, then I need negative 2. So I will write negative 2 here. This is applied always to the diagonal element, to the main diagonal element. So according to the column I am dealing with, I will look for its main diagonal element, bare column. Here we are in column 2. So the main diagonal element in column 2 is the 2, 2 element. So this one, which will be developed or will be used to eliminate the element below. And then we will directly, blindly, we can say plus row 3 or plus the element which is requested. Now, the result is to be set in row 3, which means that row 1 is unchanged. And off here 6. Okay. What about row 2? I don't like the 6. Okay. What about row 2? Row 2 is unchanged as well. The only change will occur to row 3. So row 1 is unchanged. 0, 1, 1, and negative 1. Row 3 will be 2 times row 2. So let's multiply row 2 by 2. This is 0. Times 2. This is 2. By 2. This is 2. By 2. This is negative 2. Directly now we can add 0 plus 0. This is 0. And then 2 plus negative 2. This is 0 again. 2 minus 2 or 2 plus negative 2. 0. Negative 2 plus 2 again 0. And therefore, let's watch what we have reached here. Now we have reached 1 in the main diagonal elements, right? And then 0 is below, which is great. The second main diagonal element is 1 and 0 is below. The third main diagonal element is 0, which is accepted. And now the below triangle is all eliminated. And the main diagonal elements are 1s or 0s. And this means we are in echelon form. This is what we targeted at step number 2. So we will move now to step number 3, which I told you that it will be changed according to the type of solution. And we apply the back substitution and see where it would lead us. This is the back substitution starting from bottom to top, which means starting by row 3. Let's turn row 3 into an equation. We know that the first column was x1 coefficients and the second was x2. Here was x3. This bar is equal and these were the b's finally. Okay, so this means that 0 times x1 eliminated. For the people who find it hard to imagine, so it's 0 times x1 plus 0 times x2. This is the equation. Plus 0 times x3. This is a derived equation from the original one that was given in the exercise. So in the exercise we had 0 times x1, negative 2 times x2, negative 2x2 minus 2x3 equals 2, right? The equation we have reached now is an equivalent equation. This equation is reached using the elementary row operation, which represents an equivalent system, for the given system, it's more simple and its solution is more direct. This is why it helps us in finding the solution. However, this 0 multiplication is turning into 0 equals 0. Now this situation differs than the other one. In the other problem above it, we had a false statement, if you remember this, right here. We had this 0 equals -7, and we said that is a false statement, and hence we have no solution. The system has no solution. But here, it's different. We have a true statement. And the true statement states that it's 0 equal to 0, which means that this system got to have a solution. It's a true statement, no contradiction is here. But we have still an equation for row 2. Here x1 is eliminated, and we have x2. I will tell you soon what we are going to do in this case, plus x3 equals -1. And let's read the last row, row 1, which is 1 times x1, so it's x1, minus 3 times x2, which is x2, minus 2 times x3, and then this will be equal to 6. Okay, so now we have like two equations in how many unknowns? 1, 2, and 3. We know that for solving number of unknowns, we need the same number of these unknowns equations. We need equations of the same number in order to be able to solve it. This is why we will turn about this. We will turn about this situation by assumption, or by letting a free variable, free, it's free, so it can be any value, right? Any value means it can be any value from the real numbers. This R with the bar indicates the set of all real numbers, including 0, -half, 3 over 2, 12, 1999, and so on, all the real numbers, right? I need to set another equation that states a free variable. If we get back here to the echelon form, we find that the x1 column got 1. So the x1 is called a pivot, or a leading variable. Also, for column 2 here, the main diagonal element here is 1, which means that x2 also is a pivot, or we can call it a leading variable. Leading for what? Leading for that solution, for the solution of that system, or leading for that system of 3 equations. Okay, the third main diagonal element, this is 0, which means that x3 is not a pivot. It's a free variable instead. We call it free variable, which means that the system solution doesn't rely on it. However, what this means, you don't have to memorize this. What you need to memorize is that it's not a leading variable, or it's not a pivot, and we are calling it a free variable, the x3, which means that I need this x3 to be set to any real number. I will say that it's not significant for the solution of that system. It's free, it can be any value, so we will call it t, and we can call it r, any parameter. This t is called a parameter. And also this t belongs to the set of all real numbers. So this t can be any value. As if I'm adding an equation to the given 2 equations now, because row 3 output 0 equals 0, which is a true statement, and this is very important, that the output is true statement, not false. If it was false, we were going to say that it has no solution, the system. But because it's true, we are forced to find out a solution. This system is called a consistent system. Consistent in Arabic is متماسك, or it means that it got a solution, either infinite or unique. Okay, so it has a solution. We have to work around the situation and get a solution. This is why we are assuming another equation, and let's write the solution with respect to this equation. What's follow now always happen for this type of solution that we will figure it out now. Okay, so now I knew that, that we were looking always for that vector of unknowns. We need to find the corresponding value for each unknown, right? So for x3 now we know that it is t, so I will write here t in the third place. What about the others? What about x2 and x1? This will take us back to the equations which we didn't use, that we got from the back substitution earlier in that blue line, in that blue color. So let me substitute this in row 2. In row 2 equation, this means that we have x2 plus, instead of x3 I can write t, right, equals -1, which means that x2 is what? Is -1 minus t. Perfect. So here at x2 I knew now that it's -1 plus t. Okay, now let's move to row again. Take this equation and the previous one as well, this output, and that one. So this is 1 and that is 2. Now we will take 1 and 2 in what? In the equation of row 1 that we left here. x1, I will write it x1 because I don't have any equivalent, -3 times x2, which means -3, and x2 we know from equation number 2 here that it's -1 minus t, right? And continue, -2 x3, so it's -2, and what is x3? We know that it's t, so it's t equals what? Equals 6. Now let's rewrite this in a better way. It will be x1, and here we have -3 minus 1. This means that we have here x1, and -3 times -1 is 3, right? We will move it to the other side, -3, and then -3 times -t, this is 3t. Move it to the other side by -3t, and then the -2t will go to the other side plus 2t, and we already had 6 in the other side. Let's sum this up, the like terms. So it's 6 minus 3, this is 3, -3 plus 2, this is minus t, right? So what we have now here for x1 is 3 minus t. And here we got a solution. This is the solution. We can rewrite it in a better form. It's optional to rewrite it in that better looking form, which is to have a single vector for the 3 terms and a single vector for the terms multiplied by t. So we have x1, yes, x2, and x3. This is very well. And now we know that x1 is 3 minus t, so it's 3, and the t is multiplied by -1. And x2 is -1, 3 term, plus 1 times t. And finally x3 has 0, 3 term, plus 1 times t. This is the expected solution, which makes it clear to you the type of solution. We have indicated that this t belongs to all real numbers, so this t can be any value, it can be 0. And in this example, if t is equal to 0, then the solution, I will write it like this, the x vector of the unknowns will be 3, -1, and 0, right? Okay, it will be 3, -1, and 0. What if t is equal to 1? Because we said it can be any number of the real numbers. If it's equal to 1, it will, the solution or the unknowns will be 3 minus 1, 2, -1 plus 1, 0, 0 plus 1, 1, and so on. T can be any value. T belongs to all real numbers. It can be any value. And hence, how many number of solutions we are dealing with here? What are the number of solutions that we are having? This is the infinite number of solution, right? So this is the type where we have infinite number of solutions, and we have to represent it using this representation. We need a vector for the free term, another vector for the parameter. Okay, we always know that we are dealing with infinite system of solution if we have the zero. Let me tell you about this here in the echelon form. I'm sorry, the page just turned. So here in the echelon form, yes, in the echelon form here we have zeros, zero below, right? Okay, I just want a more light color. It's that one. I want it like this. Okay, so here we have this. Okay, anyways, we have the last row. The last row is zeros, and it means that the last column or the last equation is eliminated. When we have a zero row, it means that we are dealing only with two equations, and we were supposed to find three unknowns. It means that we have three unknowns in two equations, right? And three unknowns, or if the number of unknowns is bigger than the number of equations, therefore we have infinite solution. Okay, and if the number of unknowns, this is, of course, we can observe it, and it's a theorem as well. If the number of unknowns is equal to the number of equations, we will have either a unique solution or no solution. We will have a unique solution or no solution. So these are the two cases that we will sum up them at the end. But now, after we are introduced to the Gauss elimination technique and the three types of solution, we want to introduce the Gauss-Jordan technique discussed in exercise 3. So here in exercise 3, let's take it. Let's take number. We have A, B, C, D, E. Let's take E. So I want to take the E system here in order to apply. So the question says, solve each of the following systems of linear equations, SLE, systems linear equations, using Gauss-Jordan method. So we will simply use the Gauss-Jordan method. Let's state this method first, what it indicates. The Gauss-Jordan, that scientist called Jordan, English scientist, added a very small step to the Gauss elimination method, which helped a lot in the programming of this technique or in the algorithms of this technique. So we will apply step number 1 like we did in setting the augmented matrix A of B. It's very important matrix in linear algebra in general. Number 2, we will use the elementary row operations, but instead of trying to reach the echelon form, this time we will be seeking the reduced echelon form. And what would this help us, or how it would help us? Number 3, it would help us that we have eliminated the back substitution step. We will directly read the solution. We will be able to read the solution directly. So let's apply these steps over that system here in number E. We will get first the augmented matrix, which is a matrix of the coefficients. We have how many unknowns here? 1, 2, and 3. So we have a column for x1, x1 is not in equation 1, so its coefficient was 0. It existed in equation 2 with a coefficient -1, and in equation 3 it doesn't exist. So watch it out. In equation 3 here, there is no x1, so it's 0. Okay, in x2 column, here we have an x2, so it's 1. We have x2 here, multiplied by 3. We have x2 in the third equation multiplied by -2. x3, we have here x3, it's coefficient 1. Here as well, multiplied by 2. In the last equation, it's multiplied with -2. We don't forget the or the off. It's read as off, and it means equal. Equal what? Equal to the right side, which is -1, -6, and 2. Okay, that is the system. In step number 2, we need to apply the elementary row operations in order to reach the reduced echelon form. Okay, let's work it out. Here we have 0 in the first main diagonal element. We need it to be 1. It's very easy to take this -1 and multiply it by negative, right? Because I know most of you will just say it. We have did it many times now. So we will take row 2 and exchange it with row 1 directly. Okay, so it will be here -1, 3, 2, and -6 off, and then 0, 1, 1, -1, and finally we have 0, -2, -2, and 2. Okay, very well. Now we need this negative to be 1, right? So we need to multiply row 1 by -1. You can make it in your sheet, in your solution while solving. You can just take this negative out. I mean, you can edit the matrix, the written matrix. I'm just doing it that to make sure that none of you missed any point, but you with yourself, you can write over the matrix that is given. Okay, so here we have 0, -2. This is -2, and that is 2. Okay, now we have in the first column, the first element is 1 and below it zeros, so the first column is ready. The second main diagonal element is 1, but below it is not 0. So what we need is to eliminate that element. Eliminate the -2 by adding it to what? To 2. And this 2 is multiplied with this 1, which lies in row 2. And now directly we will add this to row 3 blindly. So what we thought of is that -2 needed to be multiplied or added, sorry, it needs to be added to what? To 2. Okay, so we will multiply this 1 to that 2, which lies in row 2, so it's 2 times row 2, and then directly add it to row 3. This is the benefit of writing the elementary row operation in this technique. So if you have any question, just ask me in the tutorial, and then we can focus over it. Now using this one, we will eliminate that -2, which means that row 1 is of no change, right? So I will copy it. Row 2 is of a change? No, the change will be row 3. So here, row 2 as it is. Now, row 3 needs to be set using that arithmetic expression. So we need to multiply row 2 to 2. 0 times 2, this is 0. 1 times 2, this is 2. 1 times 2, this is 2. -1 to 2, this is -2. Now add directly. 0 plus 0, this is 0. 2 plus -2, this is 0. 2 plus -2 again, this is 0. -2 plus 2, oh, that's 0. So this is the result. Let's discuss it. Now we have 1 in the main diagonal element and below it zeros. Perfect. 1 in the main diagonal element and below it zeros. 0 in the last main diagonal element, so we will ignore this element. We will ignore this column. But that element here, that is 1, we need to eliminate above it as well because we needed the reduced echelon form. But to let you know that we have reached echelon here. So this is echelon, but we are going further to the reduced one. So this is echelon. Let's move to the reduced echelon. What we need to do is we need to use that 2 element here in order to eliminate the element above, this -3. So I will multiply this one by 3. So it will be 3 times that one. That one lies in row 2. So I will multiply 3 times row 2 and then add it to row 1. And the solution will be set where? In row 1. This is the result. This is where we are going to set the result. So you might rewrite it, write this elementary row operation by any format that will make it more convenient to you. You might write that 3 row 2 plus row 1 and then make that arrow into row 1, which indicates that this arithmetic expression result is going to be set to row 1. You might write it like this. Just make it with ease for yourself. What you find it convenience and you find it comfortable to you, just use it. It's not important how to represent it, but it's very important to indicate it. Okay, so here the change will be applied to row 1. So let me copy row 2 and row 3, the zeros. Now row 1 will need 3 times row 2. So row 2 times 3, 0 times 3, this is 0. 1 times 3, this is 3. 1 times 3, again, this is 3. -1 times 3, this is -3. We can add now into row 1. So 0 plus 1, this is 1. And then 3 plus -3, this is 0. And then 3 plus -2, that is 1. And then -3 plus 6, which is 3. Right? We have an off bar here. What we have reached is 1 in the main diagonal element, below it zeros, 1 in the second main diagonal element, below it and above it zeros, and 0 in the last main diagonal element, which means that it's negligible, and hence we have reached the reduced echelon form. The reduced echelon form is required only in Gauss-Jordan. Only if the question states solve using Gauss-Jordan. Sometimes you have a question in the exam and it tells you solve this system using Gauss elimination and Gauss-Jordan. So it's like you will solve it with Gauss, and then after finishing and getting the solution, just take the echelon form in a new step and continue to get the reduced echelon. So continue in eliminating the triangle above if you have a leading coefficient or a basic variable, and finally you will be able to read the solution. This is step number 3 that I will indicate it here. So in step number 3 we are just reading the solution. So let's read the solution again from bottom to top. So row 3 here, row 3 indicates that 0 is equal to 0 because this bar is 0. And it's beneficial to state that you had here a column for x1, x2, x3, so that we don't forget it. And then row 2 says that we have x2, and then plus x3, because it's 1 times x3 equals what? Equals -1. And that row 1, we have x1 times, because 1 times x1, x2 is eliminated, and x3, so it's plus x3 equals what? Equals 3 this time. And therefore we can state from these 3 equations that the vector of unknowns, which is x1, x2, x3, this vector is equal to what? We have x1, which is equal to 3 minus, let me write this by a different color. So from row 1 here, we can say that x1 is equal to 3 minus x3, right? And we can, at row 2 here, to write that x2 is equal to negative x3 minus 1. Why am I doing this? Notice these equations in blue, because in the column of x3, the main diagonal element turned to 0, which means we have what? A free variable. A free variable. Okay, and the free variable, we can know it as the number of equations minus the rank. Do you remember the rank? The rank of this matrix is what? The rank here, the rank is the number of non-zero rows. This is a 0 row, so it's not counted. We will count the 2. So the rank here is equal to 2. And the number of free variables, as stated in the theorem, is equal to the number of unknowns, which is 3 here, minus the rank. And the rank here is 2, so it's minus 2. So this is equal to 3 minus 2, which is equal to 1. So you have one free variable. Let's put it in a cloud, because it's a note. So here we have one free variable, which seems to be what? x3. So we will let x3, we can let it equal to t, for example, or just keep it x3, by the way. You might just keep it x3. So let's keep it this time. The last time we call it t, and we will say that x3 belongs to all real numbers. It's a free variable. Okay, and hence we have x1 as 3 minus x3, and x2 from here is negative x3 minus 1, and x3 is x3. It's a free variable that belongs to all real numbers. We can separate this vector and write it in a more convenient way, where we will take the numbers, the free terms, the numbers, the 3, from here the negative 1, and here we don't have a number by itself, a free term, so it's 0, and we will put them in a vector, plus another vector which will carry the coefficients of x3. Here we have x3 multiplied by negative 1, here we have x3 again multiplied by negative 1, here x3 is multiplied by 1, and we will say that this vector is multiplied by x3. Now this final representation for the solution is the required, and this is what is asked. You may write it like this, indicating that x3 was a free variable, and this is how we can indicate it simply. You may call it t or r or s, like you find in the solution sheet, and then you can represent the solution like that. So what is required is the vector of unknowns equal to these two vectors, because it's an infinite solution, right? Okay. I want to solve with you another exercise over the elementary, over the Gauss-Jordan, over the Gauss-Jordan. So let's take number G. Let's take number G. Just to highlight the concept, it's very beneficial to repeat it. So please solve all of the exercises in the worksheet, because it's very important for your practice and for your understanding. So that, like you see, it's very simple steps, but we have to take care and be cautious. What is before what, and where are we going, and what do we need, what do we seek in this certain step, and where are we going, and so on. So here we need to use the Gauss-Jordan as indicated in the exercise, the Gauss-Jordan elimination, okay, and which indicates the first step is to set the augmented matrix. Now we know it. We need a column for each unknown. We have here only x and y, the coefficients of x2 in negative 2, the coefficients of y is 6 and negative 6 off, which means equal what? The right side. Now we need to get what? We need to reach the reduced echelon form using the elementary row operation, because this is the Gauss-Jordan, right? So I will do this. I need this 2 to be 1, so we can just multiply row 1 by half, right? And in this case write it above an arrow. So we will have 2 times half, this is 1, 6 times half, this is 6 divided 2, which is 3, over 1 times half, this is 1 half, and then we will leave this as it is for the meanwhile, for this step. And then we need to, we have the first main diagonal element 1, perfect. We need to use that one to eliminate the element below. So we will multiply this one, which lies in row 1, by 2, and then add it to row 2. We don't have row 3. So row 1 will be as it is. Okay, and row 2 will be the result of 2 times row 1. So let's multiply here. 2 times 1 is 2. 2 times 3, this is 6. 2 times half, this is 1. And then directly add 2 plus negative 2, this is 0. 6 plus negative 6, wow, that's 0 again. 1 plus 1, this is 2. Now what happened? We have in the first main diagonal element 1, below it 0 is perfect. The second main diagonal element is 0, and hence we are not concerned by eliminating the elements, either if there were elements below or that element above, which is 3. We are not into eliminating it. Now we have reached the reduced echelon form. Let's, in step number 3, do what? Let's just read the solution. So it's not like a back substitution, not like a formal back substitution like we did in the Gauss elimination, but in Gauss-Jordan it's more easy. Again, from bottom to top, please. So from bottom we have row 2, which is, these were the coefficients of x, y, and that was the equal. So 0 is eliminated, y is eliminated, and 2. We have 0 is equal to 2. Once you find a contradiction like this or a false statement, this indicates what? The false statement is a contradiction. And it means that this system of no solution, yes. Or you might call it inconsistent. Inconsistent means it has no solution. Perfect. The last exercise here that I want to show you to you, because I want you to see that the benefit that we got from the Gauss-Jordan, the real benefit of Gauss-Jordan will appear in the last exercise. Okay, it's the last one. Okay, let's just take that here. Okay, so here we are asked to use Gauss-Jordan. I will make it very quickly. This is, we need to use Gauss-Jordan. Okay, elimination technique, which means that we need the augmented matrix A of B, which is directly, we have here x, column for x, column for y, column for z, and the equal bar. Let me write the coefficients of here of x. We have 4. The second equation -1. It's not ordered. Sometimes it comes like this. You have to take care. In the first equation, the coefficient of y -1. In the second is 1. In the third, there is no y. The z exists in the first equation. We don't have z in the second equation. In the last equation, it's 1. The right side is 7, -2, and 3. Okay. So here we have this equation. We will work it out. We will, of course, interchange here row 1 and row 2 and multiply then row 1 by negative to have this as 1, and then use the elementary row operations in order to reach the reduced echelon form, which you will find it will turn to be. So here this matrix form that is reached after applying the elementary row operations. So exactly like we did, just do it for your exercise. Interchange row 2 with row 3 and then multiply it by -1, and then you will have 1 in the first main diagonal element. Use it in order to eliminate the elements what's below in order to be done with the column 1, and then move to the second element. In the second row it will be 3. you will multiply it by 1 over 3 in order to turn it into 1 and use it to eliminate the element what's below. And then in going after eliminating the triangle below, you will move to the triangle above. So these diagonals will be 1s, and you will be done with the below triangle first, elimination, and then you will move above, because all of the main diagonal elements here will be 1. So you will need to use that one to eliminate the 2 elements above. Okay, and then this one to eliminate the element above it. And hence you will reach that format. This form, which we will reach, we can directly read the solution in if this was step 2 of the Gauss elimination. So in step 3, the reading of the unknowns, you will find that it's that easy. Just in row 3, like we used to start, in row 3, that was the unknown of x, and this column was for y, and here for z, this bar was the equal. So you have z directly equals what? -1. And from row 2, we knew that y is directly equals to 0. And from row 1, which follows x1 or yes, is equal to what? To 2. And therefore, the vector of unknowns that we are seeking, which is composed of x, y, and z, is equal to 2, 0, and -1, which corresponds to what type of solution? It's of course the unique type of solution. So in the Gauss-Jordan, we just directly read the solution, and this was very beneficial dealing with the programs or in the algorithms. I want to show you here above, where we had this system. So this is the shape of the system that we are working on. It can be extended up till nowhere, horizontally and vertically as well. Okay, the types of solution is no solution unique and infinite, like the solutions that we have discussed, but also I want you to consider this type, these 3. So here, for example, in the last shape, that one, we have 2 lines that coincide. So this is the infinite solution, right? Here we have 1, 2, 3 lines. So we have line 1, line 2, and we have line 3. The 3 lines intersect in only single unique point. So this solution is the what? Is the unique solution, and this means that we had 3 equations in 2 unknowns. Here we had 3 equations, but there is no unique point of intersection or common between the 3. So this will be resulted algebraically in a contradiction and will be a no solution. Okay, so here in the last thing as well, we need to wrap up that this above 2 matrices is what? When we have zeros in the triangle below, and this asterisk character indicates a number, a non-zero value. So if we have here non-zero value and below it zeros, in the second main diagonal element non-zero and below it zeros, the second main diagonal element it's zeros, and it turns all what's below to zeros as well, which is not required, by the way, and so on. This is the echelon. Here again is echelon. What about that one? The 0 main diagonal element, we remain the elements above. We don't have to eliminate either below nor above, by the way. And here is 0 as well, so we kept what's above. So this is the reduced echelon. This is here again the reduced echelon. The 2 above are only echelon. If we extended the geometric perspective into the equation of 3 unknowns, this means that each equation indicates a plane, like we said, and we can just represent the plane with a sheet. So every sheet of these is representing one equation in 3 unknowns, one linear equation and three unknowns, which is a11x1 plus a12x2 plus a13x3 and so on up to reaching the right hand side, which is B. If the three planes has a single point in common between the three, this is the unique solution. If they have a line in common, this is the infinite solution because it carries infinite number of points. The straight line carries infinite number of points, and hence this is the infinite solution geometrically. And if we have any of the three scenarios below here, the A, B, or C, these three planes intersect at here we intersect at three lines, so we don't have a line in common between the three. Each line is common between plane 1 and 2, the orange and the blue, and then here the common is between the orange and that tab or that light blue. And here we have another lines, but it's not common between the three of them. Here we have none. The three planes are parallel, and hence we have no solution. Okay, hope that you have got all what we have discussed. If you have any question, please let me know. Wishing you all the best of luck. Goodbye.